Hello everyone, I'm Amrit Kaur. Welcome to the lecture series of data structures. I will be covering the topic connected components and Dijkstra's algorithm. So the contents are, first I will be discussing about the basic of connected components, then we will be talking about the Dijkstra's algorithm in detail with the help of an example and a pseudocode. Connected components. Referring to connected component with respect to an undirected graph, which can be represented as G is equals to VE, where V is the set of vertices or the nodes, E refers to the edges between them that are connecting the vertices. So a connected component is basically a maximal set of nodes that each pair, say for example U and V, is connected by a path. So this can be better understood with the help of this example. So a connected component in this particular graph, as we see on whole, is represented in the form of two connected components. One is 0, 1 and 2. Here the node 0 could be U. The node 1 could be treated as V. So in this we can see these pair of nodes are connected by this particular edge E. Similarly, from 1 to 2 also there is an edge that exists in a way that all these nodes are connected either directly or indirectly. Similarly, for this connected part, that is this component, the vertices 3 and 4 are connected with the help of the edge that directly connects them. But there is no point of contact either directly or indirectly amongst any of these components. So there are two individual components present over here in this image that are represented. So using this concept of connected components, we will be discussing the Dijkstra's algorithm. In this, we are going to discover about a single connected component, that is a single graph on which we are going to apply this algorithm. Talking about Dijkstra's algorithm. Now this algorithm helps us to find the shortest path between any two vertices of a graph. It basically works with the concept that we have a source node and we have a destination. Now source and destination could be composed of several vertices or nodes lying in between them also. So we keep on traversing for the shortest path between any two pair of vertices. So this basically refers to a greedy approach, that we aim for the shortest path that is at hand for a pair of vertices, and then we start moving forward with it until and unless we reach our destination. So let us see this with the help of the example. Here in step 1, we see a graph present over here. There are nodes which are blank over here, represented with the help of blank bold circles. Then there is weighted edges, which represents the weight or basically the cost of the path. So what we do is initially we can pick up any of the node as the source node. So here we have selected this particular node as the source node. It is labeled as 0. That is the minimum weight of the source node where we are present if we consider a root. Rest of the nodes are currently labeled as infinity because we are not at the point aware about their weights or the cost, because we have not traversed them yet. We are at the starting position and then we will be aiming for the particular edge that gives us the minimum cost or the minimum weight, and as per that we are going to traverse our edges. Next, what we do is we simply see over here that in this case from 0, we look out for the connected, basically the directly connected edges, which is 4 and 4 in both the cases. There are two nodes connected with the 0 directly. So how we have to update the weight is, we simply add the weight at the current destination plus the weight of the edge, that is 0 plus 4. That becomes the weight of the node we are aiming to traverse. In this case also we have 0 plus 4 and it updates the weight over here. Since 4 is greater than infinity, so infinity is replaced by a current smaller weighted value. After this, we next move on to our further step. In this case, we realize we have two weights, that is 4 and 4. Now which path we have to pick up relies totally upon us because the weights are similar, so we can pick up either of the two. So for example, I pick up this particular path, that is from 0 to 4. After this, I realize from this particular node, there is only one node that is connected which already has a value V. Now, any updation is referred to as relaxation. So, relaxation is simply what we are doing in this. We add this value of the current node, that is 4, and the weight or the weight present on the edge to reach to the other node that is connected to it directly, that is 2. So, it becomes 4 plus 2, that is 6. And then we compare it with the weight that is already present on the node. So here we realize 4 plus 2 is greater than 6, so no updation or relaxation will be performed at this point. Otherwise, it would have been relaxed if the weight would have been lesser than the current weight of the node. So at this point, we realize amongst the two available paths, that is this particular value 4 and the particular value 2, we have to aim for the next shortest path to reach out to the next point. So here we pick up this particular edge that is weighted as 2 and traverse to the node weighted as 4. After this, at this point we realize there are 3 nodes connected to it directly. Now these nodes initially were labeled as infinity. They were having the path 3, 6 and 1. So we simply aim for relaxation operation again. So now the weights will be either updated considering the fact that they were already labeled as infinity. So any weight that would be present would be less than infinity and all of these nodes will be relaxed. So the same procedure, that is the current node weight, that is 4, the edge weight, that is 3. So 4 plus 3 becomes the weight of this node we are aiming to traverse. Then similarly 4 plus 6, that is equals to 10, becomes the weight of this particular node that is connected to it directly. Then 4 plus 1 also becomes the weight of this particular node, that is 5, which is also connected to it directly. Now amongst these 3, we have to pick up the minimum weighted edge again. So now we see that our minimum weighted edge is this particular value, which is labeled as 1. So we traverse this node that is labeled as 1 and we reach out to the destination, that is 5. In the next step, we see that we have this value at this point, that is 5. So with respect to 5 now, we have to see which are the directly connected nodes. Now we see there is only one node present over here that is already labeled as 10. So we again check for the value if it can be relaxed or no. We see 5 plus 3 over here. We realize that this value 5 plus 3 is already less than the value number 10. So that is 8. So now this node value gets relaxed and it becomes 8. So now when we have this option, we see which is the minimum weighted edge that is available to us. So now the condition is amongst the available edges, I have to pick up the minimum weighted edge. So from 5, there is only one edge, that is 3. So we pick up this particular edge. So traversing it, we have 0 to 4, that is the edge number 4. From 4 to 4, we have edge number 2. From 4 to 5, we have edge number 1. And from 5 to 8, at this point, we have edge number 3. Now, since we are always aiming for a minimum spanning tree which should not contain any cycle but should traverse all the available nodes, we see that at this point 7 is left which is not connected. So after reaching node number 8, we see that it is either 5 which is connected to it but it is already traversed. Then we have 7 connected to it which is not traversed yet. Then there is 4 already connected, so we are not traversing back at any point of time. So we will simply aim for this particular node that is not traversed yet and is already labeled as 7. We see 8 plus 2 is 10, which is eventually greater than 7. So we do not perform any relaxation operation at this point of time. And here we realize the minimum weighted edge that was traversed was from 4 from this point. So the edge labeled as 3 gets selected because no relaxation was performed from this edge. So we do not select this particular edge. So now our final cost becomes 4 plus 2 plus 3 plus 1 and 3. So this was about Dijkstra's algorithm. Let us see the pseudocode for the same. In this we see we have a function labeled as Dijkstra. Now it simply says for every vertex in the graph G, we have a graph which we can label as G. We initially assign the distance of every node as infinite as we have done in step number 1. So this denotes the step number 1. Previous is denoted as null. So previous vertex obviously refers to the initial point which we are already labeling as 0. Then we simply check for a graph that is V is not equal to S. S simply refers to the set of vertices that we have traversed. If it is not traversed yet, we simply have to move to it by keep on updating our distance values. So for this, we simply use a priority queue to make sure that which are the set of vertices that are to be traversed yet in order to realize the order in which they will be traversed. After this, as long as queue is not empty, we start extracting the minimum weighted edge for that particular node and start visiting it. After we are visiting a particular neighbor, say V of a node U, we have to perform a relaxation function. Relaxation, as I explained already, It simply adds up the distance or the weighted edge path that is lying between two vertices and the weight that is already present on the node and simply sums it up and checks for the condition. Now this is refers to as relaxation. This is the important condition that if the calculated distance is less than the already assigned distance, then we update the value of the already assigned distance to a lesser distance, which over here could be temp distance. Otherwise, we do not perform any updation. So we keep on doing these steps recursively until and unless we find out the minimum distance path, and finally we have an access to all the nodes and a minimum spanning tree is created. So this was all about Dijkstra's algorithm and the pseudocode for the same. Here are the few references. Thank you.